is a result for the cross-sectional area of any binary compact merger remnant. Now, this is a very general result. We are not alluding at all to what merged. Could be anything, could be any compact object, okay, including boson stars or gravitons. And, well, this is some technical thing about compactness ratio, and you know that the compactness ratio for a black hole is 1, and it's about 1 of 10 for neutron stars, and maybe 1,000 for white dwarfs, and so on. Now, I would like to say a little bit about gravitational wave entropy. So, the point here is that there was this objection that if you have a two-body in-spiral, it will give a monochromatic signal, and therefore there should be no entropy. However, this argument fails when you're close, because when you're close, you see you have particle crunch. When the two merging objects get closer, the gravitational field is so high that you will have something like, particle creation, which was first shown by Parker. A very dynamical space-time with matter around it will always produce particles. This is what Parker showed in 1967, and an example of that was Hawking radiation, where he discussed collapse of a star. So this largest contribution will come from this merger. We made an estimate. The estimate comes out to be about, not very much. It's about 100. Anyway, we have an estimate, and these are now the results. So this is, I should say that these results were plotted by my collaborator. I'm absolutely nowhere with the competence that requires to plot things like this. So these are the two merging, let's say, black holes, and then we have a prediction. So it's a color coding, which goes from here. This is the color coding. So you can see that this is a 3D plot, actually. This be a very, I'm marveling at this myself, because I couldn't do this myself. That's the reason for that. So you have all these areas given. This is in kilometers squared. So that's why this large 10 to the power 18, 7 that they come about. So this is about black hole merger. Perhaps the more relevant one would be this binary neutron star merger. But there, of course, the scales are very different. But this is quite the same. And the question is, what do they merge into? Okay? So here, I would have liked to get data from the observation made by LIGO and Virgo in BGW 17718, and or is it 170817, I'm sorry, which Professor Devadish Bandyopadhyay mentioned. But however, the mass measurements for the remnants are not very good at all. And in fact, there is still a debate. What do these neutron stars merge into? Now, I have heard Devadish mentioned kilonova. I've heard black holes. Some people say, oh, this is a super heavy neutron star. So again, there are ambiguities in the observations. But if we have those observations, I'll be able to compare. So this is really the minimal upper bound, this is the lower bound, the minimal bound on the area of the merged remnant. I should be able to give points and argue whether our bound is valid or not. But this is exactly what is taken. So what you do is when you have neutron star mergers, and suppose they do merge into a neutron star, so you have now predictions of how big the size of that neutron star would be. And if you're able to then formulate this, compute this R1 and R2 and the remnant radius, and compare the remnant radius from the measurement with the theory, and if it turns out that the area of the remnant is less than our minimal area, then our plan is to discard that particular equation of state as a valid equation of state. So, of course, this is what theories must do. Your result must be right, and use that to rule out other theories, other equations of state. So, the advantage of doing this, I think I've mentioned that somewhere, is that, Devadish also mentioned tidal deformabilities. That's a complicated process to take an equation of state and extract tidal deformabilities, or the other way around. I mean, neutron star physics is actually very complicated. The metric for a neutron star must involve the quadrupole moments involved. It's not like a black hole, which has very simple metric. So, it is a complicated thing.
Arthur, you have about 2 minutes.
2 minutes. I'm done. One more slide. 1 or 2 slides. So basically, I just wanted to say that there is a prediction that is possible, and therefore you can choose. You can then choose an equation of state, calculate it, measure it, and if this measurement turns out to be less than the minimal area, discard it. Okay? Now, we have not been able to do it because this is what hasn't been measured very accurately. And if you can measure it, then of course it's good. Again, I should say that this is really not exhaustive. It's proof of principle. And of course, the success depends on the accuracy of the mass measurement. Now, this is the same view. This is just how to calculate. So we tried to do this with a bunch of equations of state. However, what is missing is the column of, again, the measured values of the minimum radius, remnant radius. That's what's missing here. Now, Devadesh, of course, is much more of an expert on neutron stars, but we at least have a way of checking if whatever our predictions are makes any sense. So now I'm done. This is the summary. Obviously, we need better data, and we're going to get it. So this subject is alive. Very recently, my collaborator suggested that we look at binary coalescences involving a black hole and a neutron star and see how that checks with our results. And that's a very exciting thing. So after my teaching commitments get over, which is huge this time, I shall be able to get back to this. I think this is the first time, perhaps at least, I've been able to mention how a loop quantum gravity formulation may not be completely out of sync with what is being measured. Although it's tiny, it's probably exponentially small, but I have great faith that accuracies will go on increasing, maybe another 50 years or so. But now that we are on the path of direct detection of gravitational waves, who knows? Perhaps this will be a way of finding quantum gravity fields. There are objections that the Bekenstein bound is heuristic. So some very rigorous people like Abhay Ashtekar think that this approach is no good because it's heuristic. And my rejoinder is that there is already work by Cassini on the Bekenstein bound, which says that there is perhaps a rigorous way of establishing this bound. So I end with this little translation I made of this poem by Rabindranath Tagore in Bengali. It is, of course, Ashini Gale, Chehillole, Joar Bhatai, Bondole, Nari Temor Raktodharai, Legeche Natta. Who can beat it? Thank you very much.
Questions? But brief questions.
Thank you, Parthu. It is a very nice presentation on this type of thing. For the, there is a gorgeous telescope in Villa Planetarium. I've seen a show on that sky, and I've heard of LISA. That is in USA. That is a very, and some observatories exist in this India for this sky monitoring and all these things. Is there any telescope facility available for the commoners in Calcutta? Otherwise, than these so.
Oh no. This is like, see, when we think of telescopes, we always think of optical telescopes. But to observe gravitational waves is of course a very different activity. These are interferometers, but India is building one with the United States with LIGO. It's called LIGO India, is it? Or
LIGO India.
Yeah, and that's coming up in Maharashtra, in the middle of Maharashtra, and we expect it to be operational by 2025. So we are certainly involved. Now about LISA, yeah, that's a very good question. I wish I would know more about it. Whether it's going to be up now, there's a war going on, so who knows when LISA will be up. So I can't really answer that part.
Right. Thank you very much.
Okay, any more questions? If not, then we thank the speaker once more.
Thank you.
Thank you very much.
We can all